Hello students. So today we are going to solve the assignment number 1 of atomic structure in our Sangharsh batch. You all very well know that how can you download this assignment, and you have to solve these assignments, and then after solving these assignments at least 3 times you can come and watch this solution video to check whether or not your method is correct. So now let's start with this first assignment of atomic structure. So everything is okay? Yes. So Rutherford scattering experiment is related to the size of the, as we all know, this is everything about from Rutherford model is all about nucleus. So the Rutherford scattering experiment is related to the size of nucleus. Next one, the increasing order lowest first for the values of E by m, charge by mass ratio for electron, proton, neutron and alpha particle. So for electron, proton, neutron and alpha particle. So guys, we all know that charge can be taken as 1 for electron and 1 for proton. The mass of proton will be 1 unit. For neutron, the charge will be 0, mass will be 1 unit. And if these masses are unit 1, then mass of electron will be 1 by 1837. So we have this 1837 E by m ratio for electron. For proton it is 1, for neutron it is 0, and for alpha, the alpha particles are actually doubly ionized helium atoms. So doubly ionized means the charge will be +2, mass will be 4, this is half. So as it is quite evident, the neutron will have the minimum E by m ratio, then we have this alpha particle, then for proton, and the highest will be for electron. So the option will be N alpha P E. So this is the option number D will be the correct answer. So now the next one is Rutherford alpha particle scattering experiment eventually led to the conclusion that mass and energy are related. No. Rutherford model is all about nuclear part and extranuclear part, and along with this experiment we can easily understand that electron occupy a space around the nucleus. Second option will be the right option, as it has nothing to say about neutron. Neutrons are buried deep in the nucleus. The point of impact with matter can be precisely determined. No. So option 2 will be the right option. Now, which electronic level would allow the hydrogen atom to absorb a photon but not to emit a photon? If we try to understand the problem pretty well, so this is the level on which an electron can absorb a photon, and by absorbing photon, electron can move upwards in the quantized level of higher energy. But it cannot emit a photon and cannot go below in quantized level of lower energy. That means the electron at present is located on the lowest quantized energy level. So I think 1s will be the option. And why is it so? Because electron can go above this level by absorbing a photon but cannot go below this because this is the lowest level. So the option number D will be the right option. Which one of the following set of quantum numbers represent an impossible rearrangement impossible arrangement? So my dear students, we have to check each option. So option number 1 is n is equal to 3. For 3, we all know that L can assume a value of 0, 1, 2. M can be 0, minus 1, 0, plus 1, minus 2, minus 1, 0, plus 1, plus 2. So N3, L2, minus 2. Yes, M definitely can assume a value of plus half. Now the n is equal to 4, you can have value of 0, 1, 2, 3, as L can take values from 0 to n minus 1, and M will be 0, minus 1, 0, plus 1, and then minus 2 to plus 2, and minus 3 to plus 3. So 400, yes, 400 is applicable. Definitely half will be there. So for n is equal to 3, we can have L0, 1, 2, M0, minus 1 to plus 1, then minus 2 to plus 2. Now In this option, we have this -3 value of m, which is not feasible, which is not possible. So this is an impossible arrangement. Now the next one is, okay, this might be a typo because this option can belong to some other problem. Yes, the option number D for this will be this. So the orbital diagram in which the Aufbau principle is violated. So my dear student, we all know that Aufbau principle stated that the electron filled first in the orbitals with lower energy and then moves to the orbital with higher energy. So let's check. 2s is completely filled and then electrons are moving into 2p. As it is quite evident that this is actually, pairing is not possible until each orbital is singly occupied, which is the Hund's rule. So in first option, Hund's rule is violated, but we need to find out in which the Aufbau principle is violated. So A cannot be the right answer. B, 2s contains one electron and then, okay. So without filling this 2s orbital, electron cannot go beyond. Because of Aufbau principle, we need to fill the orbital with lower energy first and then we have to move further. So option number B is the violation of Aufbau principle. So option number B is the right answer. So my dear student, the next one is, which of the following relates to photons both as wave motion and as a stream of particle? Okay. So interference and diffraction is actually related to the wave aspect. E is equal to mc square is matter aspect. E is equal to h nu, or what we can say the Planck's quantum theory, is actually applicable for both of these. So option number D. Now the next one is a 3p orbital has two non-spherical nodes. My dear student, spherical nodes are basically radial nodes. We all know this. Okay. So if these are radial nodes, that can be calculated n minus L minus 1. Okay, I think I need to change this background color. It is not that good. Let's go with white only. Fine. So n minus L minus 1. So we can find out in case of 3p, n will be 3, L will be 1, sp will have value of L as 1, and so the spherical node or the radial node will be 1. And we have two non-spherical, no, 2 is spherical, no, 1 is spherical, and we have to find out the non-spherical also, that is angular node, and that will be the value of L, and that is for P is 1. So we have 1 angular and 1 is spherical. So option number C will be the right option. Fine guys. For a d electron, the orbital angular momentum is, again I need to change the background of this paper so that you will get a better view. Fine. So to find out the orbital angular momentum, we must know this formula as already stated in my classes. L plus 1, this is orbital angular momentum, and if you are looking forward for a spin, then you will replace this L with S, and as we all know that multiplicity is 2s plus 1. So this is what, in this case, the orbital angular momentum for a d electron. For d we have L value as 2. So 2 plus 1 h upon 2 pi. This is under root 6 h upon 2 pi. Clear, my dear student? So option number A. Now the electronic configuration of an element is 1s square, 2s square, 2p6, 3s square, 3p6, 3d5, 4s1. Okay. So this is quite evident that this is the electronic configuration of chromium. And as we all know that these are the, what you generally believe that these are exceptional electronic configuration. But there is no exception in this. And why is it so? You know what? We know that everything in chemistry is related to going from less stable state to more stable state. So as chromium is more eager to go and acquire the more stable state, it's better for the chromium atom to acquire this half-filled status, because half-filled and more fully filled are more stable. So that is why this is the ground state of chromium rather than an excited state. Okay, so this is the ground state for chromium, and for copper this will be 3d10 4s1. Fine guys. Next one is the kinetic energy Again, we need to change the color first. The kinetic energy of an electron in the second Bohr orbit of a hydrogen atom is, so what is given, n is equal to 2 in this case, and a naught is the Bohr radius. So the radius will be a naught n square by z. Okay, so this is what the concept is, because we all know that 0.529 n square by z angstrom will be the method, the formula to calculate the radius. And you all know that in one of my lecture I've explained that how to derive these formulas. If you want me to repeat that again in English, then you can type your say if you really want to for me to make a video in English for Bohr derivation, I can do so if you type this request in a comment box. So now the next one is, we need to find out the kinetic energy. So as we all know that kinetic energy is half mv square. So let's find out velocity first. So velocity can be, we know that mvr is equal to nh upon 2 pi. Velocity will be nh by 2 pi mr. So v square will be n square h square upon 2 pi. Okay, so let's solve this also. 4 pi square m square r square. Now put this velocity here, or else you can replace this with r with this a naught n square by z. So n square h square upon 4 pi square m square a naught n square by z whole square. So it comes out to be n square h square 4 pi square, and then m square 4 pi square m square a naught square n raised to the power 4, and again z square. So z square can move upwards. Okay, and as this is in hydrogen atom, z will be 1. So this is what the whole scenario is. You can cut this, you can make this 2, and you can cut this. Okay, fine. So now we have this h square, the velocity. Okay, so the velocity square is h square upon 4 pi square m square a naught square n square. So now what we can say, that if you want to put this more, this n is 2, so this is 4 pi square m square a naught square, and then we have 4. So my v square will be this much. Put this value into this. So my kinetic energy will be half of m into h square upon 16 pi square m square a naught square. So now we can easily suggest that this m will definitely be like m. So h square upon 2 into 32. So what we can do, 32 pi square m a naught square. So this is my kinetic energy. Find out if some option matches with this. 416 a square m a naught pi square. So this is C, option C. So I believe that this is pretty much clear with everyone. So now next problem is, P is the probability of finding the 1s electron of hydrogen atom in a spherical shell of infinitesimal thickness dr at a distance r from the nucleus. The volume of this shell is 4 pi r square dr. The qualitative sketch of the dependence of P on R is, as we all know, in my previous lecture, the last lecture in which I was discussing wave mechanical model, I told you how to draw these graphs, and with that knowledge you can easily predict that D will be the right option, because it is 4 pi r square dr radial probability density, lower to higher, and without touching this 0 axis, as we are talking about 1s. So 1s will not have any radial nodes. Now let's talk about the subjective problems. Let's discuss these problems. So my dear students, estimate the difference in energy between first and second Bohr orbit for a hydrogen atom. Okay, so first of all we need to find out the energy difference del E. So del E is E2 minus E1. So that comes out to be 13 pi 5 EV, and we're talking about the hydrogen atom, forget the Z, and this is 1 by N1, that is 1 to 2, so 1 square minus 1 by 2 square is 4 EV. So this is the energy difference, pretty easy to understand. At what minimum atomic number a transition from n is equal to 2 to n is equal to 1 energy level would result in the emission of X-rays with this? Pretty easy to understand. You know that V bar, we have explained it in my videos. This is R Z square, and Z is again 1 because we're talking about this is something else. With which hydrogen atom, like, okay, so then we have to find out R Z square 1 upon N1 square minus 1 upon N2 square. These V bar is actually 1 upon lambda. R is 109677. Z we need to find out because hydrogen atom like a species. Okay, lambda is given, and N2 to N1. So that means 1 upon 1 square minus 1 upon 2 square. And lambda is this. Apply this value here. You can easily find out Z, and Z is going to be the atomic number of that atom. Fine. Okay. So we need to find out the hydrogen like a species, and it is pretty easy to understand. This problem can be solved like this. So now iodine molecule dissociate into atoms after absorbing light of 4500 angstrom. So iodine atom will be broken down into 2I by absorbing 4500 angstrom of wavelength. Okay. If one quantum of radiation is absorbed by each molecule, one quanta is absorbed by each, I2 to break down into 2. Calculate the kinetic energy of iodine atoms. So we need to find out the kinetic energy of iodine atoms, and bond energy of I2 is this much. Pretty easy to understand. That means it is something sound like that photoelectric effect. And why is it so? Light is coming in with this wavelength. So Hc upon lambda is binding energy, that is the bond energy of I2, that is the binding energy, or H nu naught is given as this, but this is per mole. So we need to find out, actually this is in terms of per mole, but we have to find out in terms of one molecule. So what we can do, we will divide this 240 kilojoule per mole with this 6.022 into 10 raised to the power 23 to get the bond energy of one molecule. Find out this and then try to solve. Okay, so this is the value which we have to put it here. Okay, then this is again we need to find out the kinetic energy. You put this value here, you put this value of photon at this point, and you will get the kinetic energy. But let me tell you, what you will get the kinetic energy of one molecule. Okay, so after getting this energy divided by 2, because we have to find out for the iodine atoms. So this is how you can solve this. Okay, now consider the hydrogen atom to be a proton embedded in a cavity of radius A0, Bohr radius. Okay, it's pretty easy. Whose charge is neutralized by the addition of an electron to the cavity in vacuum infinitely slowly. Estimate the average total energy of an electron in its ground state in a hydrogen atom as the work done in the above neutralization process. Also, if the magnitude of so we have to calculate the average total energy. It is simply what this question want is a derivation of energy given by Mr. Bohr. So you have to derive the En. Okay, already stated in one of my lectures. You can watch that lecture again. Fine. And you can derive the total energy dimensions. Now calculate the energy required to excite. Again, I need to change this. Okay, so calculate the energy required to excite 1 liter of hydrogen gas and 1 atm, and then again it is pretty easy. Again 1 liter at 1 atm, and what you are getting, again it is similar to this problem which we already discussed. That means we have to find out 1 liter of H gas at atm, so you can find out the number of mole, and then the energy of HH bond is given, and basically the number of mole is given. This is per mole. You can easily find out how many moles can be in this. Now wavelength of high energy transition. High energy means going from 1 to infinity. Okay, High energy transition is this. Calculate the corresponding wavelength of He atoms. Very easy to understand. Wavelength, that means 1 upon lambda, that is r z square 1 upon, this is what moving towards the infinity, so this r z square will remain same, and we have to find out the wavelength. In this case z is 1, in case of 1 upon lambda is basically okay. High energy transition is 92. This wavelength is given. Okay, this is for hydrogen. 1 r is constant. Then in case of what, helium, we need to find out. Okay, so helium atoms will be high energy transition, the corresponding wavelength we need to find out. So wavelength is given, you can find out the r, radiation is this, so you can divide it and simply find out the corresponding wavelength of helium. Fine. Or you can easily assume that this r is constant, this factor is constant, so 1 upon lambda is actually directly proportional to the z square. So now we can use this relation and we can solve it like this. Lambda hydrogen upon lambda He is that ZHE square upon Z hydrogen square. So now you can find out. You can have this 2 square is 4, this is 1 square, you have this, you can find out del He. So del lambda H upon lambda He del, because I have to consider the calculus in case of thermodynamics in my previous lecture, so that was resonating in my mind. So this is lambda H upon lambda He, and this is ZHE, that is 2 square, and this is 1 square, so you can easily find out the del He, again del lambda He is lambda H by 4. You will get it. Fine. So the value is given already. You can find out. Now the Schrodinger wave equation for hydrogen atom is given, where A naught is Bohr radius. If the radial node in 2s be at this, then find out. Pretty easy. When we are talking about the radial node, so that means the probability of finding electron will be 0. So you can square this whole scenario, then this will be 0, put this one 0. But even in this case, this one is 0. So finally you can find out that 2 minus r naught upon A naught will be 0. Okay, we were talking about at radial node. So it's very easy. 2 is equal to r naught upon A naught. We have to find out r naught in terms of A naught. So r naught is equal to 2A naught. Very easy. The problem seems to be pretty difficult, but it is quite easy. Okay, because as we all know that at radial node, the probability of finding an electron will be 0. Now find the velocity of an electron in first Bohr orbit. We all know 2.18 10 raised to the power 6 meter per second. By that derivation, it is already been stated in my lecture. Also find the de Broglie wavelength. If you have this velocity, you can easily find out h upon mv. And then find the angular momentum of 2p orbital. Oh, very good. 2p orbital, angular momentum, orbital angular momentum, already stated. Under root p is 1 plus 1 h upon 2 pi. So this is 2 into, so h by pi is going to be the answer. Fine. So I believe this is, yes, finally we have this. Match the following thing. So according to Bohr's theory, En is total energy, Kn is kinetic energy, okay, Vn is potential energy, and then radius of nth orbit match the following. Okay, so Vn by Kn. Okay, so as we know that Vn, let me change the color first. Vn is the potential energy. Fine. If Vn is the potential energy, that means that is, we all know that kz E square upon r with a minus sign, because electronic energy, potential energy is always negative. And we have to find out the Kn. This is the kinetic energy. Fine, kinetic energy. This is half of kz E square by r, as mv square will be kz E square by r, again from the derivation. And this is why that video in which I have explained the Bohr atomic model and derive each relation like energy, velocity, orbital frequency and other things. So you need to watch that. Now what we need to do, Vn by Kn divided this will be gone, minus 2. So for A R, if radius of nth orbit is this, okay, then what will be the x? Okay, pretty easy. I have explained in that lecture only. En is equal to minus 1 by n square. Okay, so nth orbit radius, sorry, no, this is what the En, and we need to find out the radius itself, and then this is the energy, and radius will be, radius of nth will be in terms of energy. Can you find out? Even in the previous problem we have done this. Very easy. Yes, radius is a naught n square by z. This is constant, so radius is directly proportional to n square. So that means if we have to find out in terms of energy and radius, so this can be with the radius, so this is going to be the minus 1. Pretty easy to understand. Okay, fine. How is it so? En, as this is, so En is equal to minus 1 by r. R will be on this side, 1 by E1, e raised to the power minus this one, the minus 1. Fine. So this is how you can do. Okay. So now, okay, it takes a whole lot of time. Fine. So angular momentum in lowest orbital. Lowest is what? Lowest is what? 1s. So angular momentum in lowest will be 1s. S is 0, so it will be 0. Apply this now. 0 is 0 then. And 1 upon Rn is this. So y will be, only one option is left in this case. You can easily find out, n square by z. So radius in z power 1. Fine. Now orbital angular momentum of the electron in a hydrogen-like atomic orbital. Okay. So it has to do with the orbital angular momentum with L, Q. Fine. A hydrogen-like one electron wave function obeying Pauli principle. Oh, that means we are talking about hydrogen-like one electron wave function obeying. So it can be principal quantum number. It can also be azimuthal. It can also be magnetic or a spin. All 4. B is related to all 4. Shape, size, and orientation. Shape, size, and orientation. So it's first 3. Probability density of electron at the nucleus in hydrogen-like atom. Probability density has to do with this first 2, principal and azimuthal. In hydrogen-like, basically probability density is actually dependent on principal quantum number, but for hydrogen, and for hydrogen-like it will be PQ. Okay, so this is how you can solve all of these problems. This is the video solution, and hopefully now you can solve the next assignment number 2 for atomic structure. Very soon I will be coming with that also, before this Wednesday. Okay, and this Wednesday we are going to start with, yes, you're right, states of matter. Pretty important aspect. Okay, thank you guys.